All right, so picking up where we left off, finding the area of a triangle again. Fully aware that we know how to find the area of a triangle. Again, area is equal to 1/2 the base times the height. And we're not talking about matrices taking the place of finding the area of triangles. Again, if you have, like the example we talked about in class and maybe even on the first video, if we had this triangle, absolutely keep using this formula the exact same way that we've been using it for years. What we're talking about, though, is not this triangle, but instead if we had maybe this triangle, where we don't have any perpendicular sides, we don't have any side lengths, we would have a lot of work ahead of us. Doing the distance formula to calculate the side lengths, determining where an altitude was going to be located. Again, we'd have to sketch in an altitude that's perpendicular to the opposite side. That distance formula, again, the point we're trying to make is that would take a lot of effort. So luckily, we're just introducing this whole idea that if given 3 points, we could set up this matrix and we go from there. So again, assuming that we're given the 3 points, x1, y1, x2, y2, x3, y3, we could load those into the matrix accordingly. But with 3 coordinates given, each containing an x and a y, that's a total of 6 elements. We can't make a square matrix out of 6 elements. So that's why, again, we got sort of a clever hack that we could create a third column all with positive 1. Again, this way, when we're calculating our determinants, multiplying down, multiplying up, we're not going to affect anything for multiplying by 1. So, again, this is the setup. The other thing that's worth pointing out is the plus or minus symbol that's out front. Again, pretty certain that knowing our original or most basic formula, we understand where the 1/2 is coming from. But again, that plus or minus out front, up to this point in your math careers, when we see plus or minus, we're thinking 2 answers. But not so in this particular case. In this case, it's a little bit more abstract than that. Essentially, what we're running here is an absolute value, but it's going to be our decision. Are we going to opt to use the positive 1/2 as a scalar or the negative 1/2 as a scalar? We know that when we calculate the determinant, our answers have been either positive or negative along the way. So understanding that area must be positive, again, that rule hasn't changed since geometry. Again, there's no such thing as calculating a negative area. So for our purposes, if we end up calculating the determinant and realizing that it's positive, then we're going to use the positive 1/2. If we calculate and figure that the determinant is negative, then we're going to use the negative 1/2. It's the negative 1/2 times the negative determinant will put us right back to a positive area. All right, so showing what that looks like after that explanation. There, that was out too far. There we go. All right, so this time if we're giving the coordinates 1, 1, 2, 3, and 3, 2. What we're claiming is that we're going to multiply by a scalar either positive or negative 1/2. We're uncertain at this time because we know that our area is going to be either positive or negative 1/2 times the determinant of this matrix. Well, right now we can't find the determinant of the matrix if it's going to be a 3/2. So we have to create that third column, all positive ones. So now our entire focus is going to go on finding the determinant of that 3/3. So the way that we do this, we copy the columns, and we get to work. So my determinant is still going to be the sum of the downs minus the sum of the ups. So we're looking at this, 1 times 3 times 1, 3, 1 times 1 times 3, 3, 1 times 2 times 2, 4, 3 plus 3 plus 4 is 10. Multiplying diagonally going up, 3 times 3 times 1 is 9. 2 times 1 times 1 is 2. 1 times 2 times 1 is 2. And some of the others, 9 plus 2 plus 2 is going to be 13. So my determinant, 10 minus 13, is negative 3. And that's going to tell us that we're not going to use the positive, but instead the negative 1/2 is the determinant. Because negative 1/2 times negative 3 is going to tell us that the area is now positive. 3/2, 1.5, 1.5, whatever it was that we needed to go with. Again, over there on the right, if we would have obtained a determinant that was positive, then absolutely we would have used the positive 1/2 as a scalar. Again, at the end of the day, our area must be positive. All right, next thing that we can do here, again, when testing for collinear points. So just as a reminder, it's been a while since we've heard this term collinear. Collinear is just a fancy way that we'd say that if you have 3 points that are all on the same line, they're said to be collinear. If you have points that are not on the same line, they're said to be non-collinear, or they are not collinear. All right, so please understand that just looking at the setup of this particular problem looks really, really, really similar to what we had back here in terms of the matrix. In fact, it's identical. So again, given 3 points, x1, y1, x2, y2, x3, y3, we're going to build this matrix, and we run into the same issue as before. 3 vertices, 6 total elements, can't create a square. So same hack as we used previously. We're going to put all positive ones in that right column. Now we have a 3 by 3 matrix. So understand that we're actually just using the exact same formula. It's the situation that we have in front of ourselves is that if we were to calculate, given 3 points, if we were to calculate the area, say of these 3 points, calculate the area, and we realize that it's 0, the only way that that area is 0 is if all 3 of those points happen to be in the same line. If this point is not on the same line, then I guess there would be some sort of an area present. All right, so again, it's just a variation of what we had done previously. Again, please don't overthink this or overcomplicate this. So once again, it's all in the setup. We're going to create x1, y1, x2, y2, x3, y3 in the matrix, fill that right column with all ones. And really, essentially, all that we're doing is we're testing to see, is this equal to 0? If it equals 0, yeah, they're collinear. If it's not equal to 0, no big deal. The 3 points are not collinear. They're creating a triangle. Okay, so let's go ahead and try that. I accidentally put the same example on there twice. So we're saying that -2, 1, 1, 7, 5 to make it a square matrix. We're going to leave or fill in with all positive ones. All right, so -2, 1, 7, -2, 1, 5. We're going to calculate the determinant. Still sum of the downs minus the sum of the ups. All right, so as we're multiplying diagonally going down, -2 times 1 times 1, -2, -2 times 1 times 7, -14. 1 times 1 times 5 is going to be 5. So as we're looking at this, -2 minus 14, -16, plus 5, -11 is the sum of the downs. Multiplying diagonally going up, 7 times 1 times 1 is 7, 5 times 1 times -2, -10, 1 times 1 times -2, -2. 7 minus 10 is -3, minus 2 is -5. So if we clean this up, -11 minus -5 is going to be -6. So as we're looking at this, D was supposed to equal 0, instead we got -6. All that tells us is that these points are not collinear. No big deal, again, they're just not collinear, which means that the 3 points would create a triangle, which means that there would be an area if we decided to go that route, which we didn't need to, but that's how it would play out. All right, so trying that again. We're to test. Does 0 equal? Again, we have 3, -1, 0, -3, 9, 3. Not a square matrix until we fill that column with all ones. All right, so copying my columns over looks something like this. My determinant, again, sum of the downs minus the sum of the ups. And 3 times -3 times 1, -9. -1 times 1 times 9, -9. 1 times 0 times 3 is 0. So the sum of the downs is going to be -18. Multiplying diagonally going up. 9 times -3 times 1, -27. 3 times 1 times 3 is 9. 1 times 0 times -1, 0. Also gives me -18. So in calculating -18 minus -18, now we have it. D is 0. We get the target. So yes, these are collinear. All right. Last type of problem that we have, the one that we did not get to in class. Again, very, very similar. This time we're given 2 points. And we want to write the equation of the line that passes through the 2 points. So again, this is something that we've done thousands of times, maybe hundreds of times, throughout the course of, I don't know, since Algebra 1. Again, we did this back in August, even in this class. Again, it's a skill that is really, really important. Find the slope between the 2 lines. Again, we could plug in for, one of the coordinates for x and y. We can work backwards, solve for b. Using matrices now, here's another way to go about it. So the difference is that if I'm given 2 points, again, x1, y1. We're going to fill here in that second row, x1, y1. The second point, x2, y2, we're going to fill in that third row, x2, y2. So what might seem a little weird is we're going to leave the variables x and y. Again, really want to paint the picture that we're doing the same thing. Again, very, very similar. We're just going with the fact that these 2 points, x1, y1, x2, y2, if we're writing the equation between these two lines, they definitely are going to lie in the same line. And so is this third sort of generic point xy. It's going to lie on that line. So that's the reason why we can get away with saying that, yep, its determinant is 0. So when we go through the process of sum of the downs minus the sum of the ups, calculating the determinant, what we're going to create is an equation. So this is all about the setup. Once again, we're going to say that 0 is equal to, all right, we said that x goes here, y goes here, positive 1s down that third column. So -3, -1 is my first vertex. +3, +5 is my second vertex. Our job is going to be to calculate the determinant. So no different. I know that we have some variables in there, but it's no different. We're still going to before multiplying, we're going to have to copy that first column over, copy the second column over, like this. So again, our determinant is going to be the sum of the downs minus the sum of the ups. All right, so as we are calculating, x times -1 times 1 is -x. Y times 1 times 3 is 3y. 1 times -3 times 5 is negative. So typically at this point, what we're able to do is to combine like terms and get down to one single value. Not the case here. The best we can do is to say that the sum of the downs is -x plus 3y minus 15. Might seem a little weird initially, but give us a minute. Multiplying diagonally going up, 3 times -1 times 1 is -3. 5 times 1 times x is 5x. 1 times -3 times y is -3y. All that I'm going to do differently is just change the order so it matches what we had in the first. So I'm going to call this 5x minus 3y minus 3. Now another difference here is that we aren't trying to figure out exactly what the determinant is equal to. We're told that, hey, right there, yeah, the determinant, it is 0. So I'm going to change that up a little bit. I'm going to say that 0 is equal to all that algebraic stuff that we have over on the right. So if you're thinking that we have a trinomial minus a trinomial, I have to distribute that negative. I agree with you. We have -x plus 3y minus 15. Distributing, we can call that minus 5x plus 3y plus 3. And when I combine like terms, 0 is equal to -6x plus 6y minus 12. So a lot of different ways that we could present our answer. I'm going to go with standard form first. If I were to subtract the x and the y over, that's going to put us at 6x minus 6y equals -12. Noticing, of course, that we can factor a 6 out. When I divide both sides by 6, that's going to leave us with x minus y equals -2. So if we're looking for standard form, got it. Could we go from here to slope-intercept form? And the answer, of course, is yes. Basically, all we have to do is go y by itself. So if I were to add the x over, most basic, if I were to actually subtract the x over, I think I misspoke there, sorry. That puts us at -y equals -x minus 2. Almost there. I'm going to divide everything by -1. So y is equal to +1x plus 2. There's our slope-intercept. Okay. So again, I know that it looks weird, it looks challenging, but I can't stress enough. The most complicated part is doing the determinant, which for the last couple of days now, it has been a strength. All right, so the goals that we had in mind, again, by the time you walked out of here, again, I felt like we knew how to do Cramer's rule. We could do that inside and out. Students will be able to use determinants to find the area of triangles. Again, I felt like the example that we got through in class today, that probably put us there. Goal number 3 might continually be a work in progress. So again, for that reason, we're going to continue to talk about that a little bit more tomorrow in class. But homework assignment on page 591 should give us a chance to practice. Again, there are a couple of these that are going to require us to find the equation of the line. We want you to give that your best shot. But again, more to come on this tomorrow.